Hi there, folks. In these, what I think is going to be two videos, I wanted to give you a concrete model in which we can try to understand what a field is about. In other words, what is a field theory? And the way I want to do that is to analyze the model of just a simple string that is sort of stretched out in the x direction and is free to wobble in the y direction. And we'll figure out the equation of motion for this string and try to identify the string position as a field. So in this model, let's imagine that we're going to model a string as a bunch of masses, each with the same mass, m, and they're all spaced out in the x direction by a distance a. And this, this keeps going on. Let's assume it keeps going on forever. And in between the masses, we have to imagine that they're connected by some kind of little string that is itself massless. And so I'm going to represent that with a sort of black line here. And there's a certain amount of tension T in that string. So this model has three parameters, namely the mass of each mass, A, the separation between the masses, and the tension T. And we're hoping to be able to derive an equation of motion for a phenomenon that we already know about, which is if you pluck a string, you can notice that a pulse will travel from one end down to the other at some speed, right? It travels like a wave. And so already we should be able to figure out what the wave speed would be, at least what the order of magnitude of that wave speed would be just from these three parameters. So in fact, that's something that you should probably do. You should probably pause the video and ask, how can I form a speed from the parameter m with units of mass, a with units of length, and t, which is units of force? We're going to derive it though. So that's the model that we're going to use. This is stretching out in the, we'll call this the x direction, and this is the y direction. And I'm just going to say that the masses are, we're going to imagine that the masses are confined to only oscillate in the y direction. You have to, maybe there's some little tiny rail system set up for the masses just to go up and down. Okay, all right, that said, we can figure out what the forces are on any one of these masses, and what we're going to do is count the masses as we go. So this might be the ith mass, and then this might be the I plus 1th mass, and this one might be the I minus 1th mass, and imagine that there are n masses and we're going to count them all up, but we want to focus just on the ith mass here. So let's do that. Let's focus on that one and indicate, this is the y direction, and imagine that we've got our mass here, and as I've drawn the original picture, everything is at a location of y equal to 0, but once the thing starts oscillating, it'll be somewhere else. So we imagine that ith mass has a position y subscript I, and yeah, it's going to depend on time, but I'm going to suppress that. Let's just imagine that the I minus 1th mass is somewhere that's like, I don't know, maybe down here, something like this. This is and it has a height, right? It has a height of yi minus 1. And there's the I plus 1th mass, which is somewhere else at some other arbitrary height, and I don't know, I'm going to try to represent that like, maybe like this. They could be below, they could be above, but this is at least a concrete example. And of course I should have made them blue, but I think you get the idea. If that's the location of these masses, then we can figure out how much force is acting on that ith mass, because we know, due to the interaction, all these masses are connected by a string, the I minus 1th particle and the ith one will feel a force, and so you feel like this one over here will provide a force that pulls on the ith mass in this direction. Oops. Like this. That of course only has a component of force that goes down, And likewise, this one pulls on it that way as well, and it has a component that might be, like that. So let's zoom in on this one. Let's focus on just the, we're going to talk about the force on I from the I minus first. I'm not sure what to call it. I minus first minus 1th mass. And we'll do the same thing for the I plus 1th mass. That'll be easier to do once we've worked out the kinks here. So the free body diagram that I would draw here would be, okay, here's the mass, and there's a tension that I'll put in green. It's going down at some, direction like this. That's T. That's the tension in the string. And there's a vertical component to this that I'll call Ty. That's the only thing we care about. Remember, the mass we're assuming is just forced to move only in the vertical direction. We can figure out Ty if we also know, this angle, or we know the sine of that angle. Okay, apparently, so Ty should be given by, well, it's T times the sine of that angle, and probably what we need to do is be careful. We're going to include a minus sign later on. If this is the arrangement, then we'll have to put a minus sign, but let's see what happens. So this is equal to the tension times the sine of that angle. Well, if you focus up on this picture, the sine of that angle is determined by the opposite side, which is simply yi minus yi minus 1, and divide that by the hypotenuse, which is the square root. Since this side length is a, the hypotenuse has a side length of a squared plus yi minus 1 squared, and take the square root. And that's all seemingly complicated. We're going to assume that the spacing between the different masses is much bigger than any kind of relative difference in height between any of the masses. So we're going to assume that this is always going to be true. And so the tension in the y direction, or the y component of that force, is simply tension times yi minus 1 and divided by a. If a squared dominates the thing underneath the radical, then that's approximately a. And the last thing to do is actually put out a minus sign here, and I'll box this. The minus sign tells you that if yi is bigger than yi minus 1, there should be a force that's pulling it down, right? Because that one to the left of it is lower, and so that should be pulling it down. And if it's higher, if yi is less than yi minus 1, then it goes the other way. Okay, well, that's also going to be true for the I plus 1th mass as well. You can go through this logic here, and I'm going to label this one. This is the y component of the force. Y component of the force from the I plus I minus 1th, and if we did this, we would get it for the next one over, T, and yi plus 1 minus yi, and divided by a. Okay, good. So that's what we would have. We'd have to add up those two y component forces, and that would tell us how much force is either pulling that ith mass down or up. We would then use Newton's second law, and that would say, well, the net force, that is to say this one, the y component of the force from the left, plus the y component from the force on the right, that is equal to the mass times the acceleration of that ith particle. In other words, m times yi double dot, the double time derivative, and that would be Newton's second law. Okay, well, if you start cleaning things up, you put this together, what you'll notice is that you can factor out a total tension from the whole thing, and the yi plus 1, I think, in fact, I'm going to start with this one first. The order doesn't quite matter. But if you notice, what you can do is put the I yi plus 1 to start, and then subtract off the yi and put that all over a. And then the next term, you can write it with a minus sign out front. I'll put parentheses around this. And write this as yi minus yi minus 1. I'm writing this in a suggestive way. You can also, if you want to pause, verify that this is what you get when you add up those two forces. Now, I'm writing this in a suggestive way because what we want to do is we've started off modeling the string as a bunch of discrete masses separated by a distance a, but we would like to let that distance a get very, very small. In fact, we want to let a approach 0, and we're going to do that in such a way that we want, let's see, so we want a to approach 0. We're also going to let the mass of each little thing approach 0 as well. But the combination of them, what I'm going to call mu, the linear mass density, this is the mass divided by a, this will be a constant. Okay, so we're going to let that happen. But as we do that, we will also identify yi, the vertical location of that particular mass. That'll be identified with y of the continuous variable x. And what that means would be something like yi plus 1 would be identified with y at x plus a, for example, etc., etc. Okay, so that's what we mean as we make the correspondence between the discrete variables and the continuous variables. Okay, well, that is useful because if we're going to let a be very, very small, then something like this, yi plus 1 minus yi over a, okay, we're going to bring this down now. This is tension times, y of x plus a minus y of x over a. That should hopefully look like a derivative to you. From that, we'll subtract off y of x minus y of x minus a over a. Those things look a lot like derivatives. Y of x, unfortunately, I seem to have forgotten, y is a function of x, and it's also a function of time, and that's probably something I should just go ahead and add right now. T. T, you probably get the idea. So what is happening here is we are basically approximating these things as these are basically first derivatives. This is something like the partial derivative of y with respect to x, and this is going on, roughly speaking, it's somewhere between x and x plus a, so this is like, at a value of x plus a over 2. This is like the partial derivative of y with respect to x evaluated at, x minus a over 2, somewhere between x and x minus a. We're taking the difference between those two. And so what we can do is then, therefore, write this as t times I'll just simplify notation, write this as y prime at x plus a over 2 minus y prime at x minus a over 2. I'm suppressing the fact that it also depends on time. I've gotten lazy. And then, what I'm going to do is do a clever little jujitsu move, which is to divide all of this by a and then multiply it by a out front so that I haven't done anything too mischievous. X double dot with respect to y double dot with respect to x. Okay, and now I'm just explicitly writing the fact that there's time dependence there. Okay, now that I've done that, you could hopefully convince yourself, again, not being incredibly mathematically rigorous, we'll let a go to 0 soon enough. So probably what I should do here is, if you want to be snooty about it, we'll say this is approximately true. This is like taking the derivative again of y prime. In other words, this is approximately y double prime evaluated at x, because now we're somewhere between x minus a and x plus a. And now I'll just be a little more careful and write in the fact that the time is there as well. We imagine that we've made a so small that this is approximately true. Lastly, I'll take the a to the other side, so it looks like t, y prime prime, in other words, derivatives with respect to x. This is approximately equal to m over a, y double dot, x and t. And remember, what we have said is that we're letting a go to 0, m go to 0, but in such a way that their ratio is constant. So this turns into mu, the linear mass density, the amount of mass per unit length, times the time derivative of y with respect, double time derivative of y. Okay, so actually, I'll finalize what we have here. If I divide by t, then what we have is y prime prime is equal to 1 over, I'm going to call this cs squared times y double time derivative. And I'm going to box this. This, in fact, is a wave equation, something with two spatial derivatives equal to something with two time derivatives and some proportionality factor that really represents or has to do with the speed of sound in that medium, or the speed of the waves. Here, the speed of sound, or the speed of that wave squared, is given by the tension divided by mu, and hopefully, this is what you would have guessed if you paused the video, this is the only thing that you can construct out of the tension, the mass, and the separation between the masses that has units of speed, or in this case, speed squared. So the speed of a propagating wave grows with the tension of the string. That is true. It's certainly been true in my own experience, and it also grows if you make the amount of mass per unit length smaller. So that is a wave equation, and perhaps you already know that this kinds of solutions to an equation like that, y of x and t, can be written in a number of ways, and well, I'm not going to bother to write them down. What I'll do in the next video, though, is talk a little bit about the interpretation of the position of the string as a function of x and t, and interpret that as a field, and we'll talk about the kinetic energy and the potential energy of that field.